Let me pose a seemingly straightforward question to you. When one object influences another, what's actually happening beneath the surface? I'm not asking about the outcome itself, but rather the underlying mechanism. Consider this scenario. When I slide a book across a table surface, the process appears quite clear-cut. There's physical contact between my hand and the book. Direct touch. Nothing mysterious about it whatsoever. But let's complicate matters just slightly. Picture placing a magnet in proximity to a piece of iron and watch as the iron begins to move toward it. Here's the puzzling part. Nothing physically touches that piece of iron. Between them lies what appears to be completely empty space. Yet, undeniably, something just occurred right before our eyes. This observation raises an unavoidable question that demands our attention. What exactly traversed that seemingly vacant space between the two objects? Throughout history, people found this question deeply troubling and uncomfortable. Most preferred to sidestep it rather than examine it too closely or carefully. The traditional understanding was appealingly simple and intuitive. Objects exerted influence upon each other through direct interaction. One thing would somehow reach out across the void and pull another thing toward it. However, when you pause to slow down your thinking and truly insist on comprehending the actual mechanism at work, this comfortable picture starts to crumble and wobble. How exactly does the magnet become aware that iron is present nearby? Does it transmit some kind of signal or message? And if such a message exists, at what velocity does it propagate through space? Furthermore, through what medium or substance does this message actually travel? This fundamental discomfort wasn't exclusive to magnetic phenomena alone. The force of gravity presented precisely the same conceptual problem. The Earth exerts a pulling force on the Moon, while the Sun pulls on the Earth. And fundamentally, everything in the universe pulls on everything else with varying degrees of strength. But the crucial question remains: how does this actually work? Isaac Newton himself, the brilliant mind who mathematically formulated the law of universal gravitation, felt deeply troubled and uneasy about the concept that one object could somehow act upon another across the emptiness of space without any intermediary substance or mechanism. He performed his calculations brilliantly, predicted celestial motions with perfect accuracy, and then candidly admitted with refreshing honesty that he genuinely did not understand the fundamental mechanism by which gravity actually operated. The fact that gravity worked was sufficient for computing planetary orbits with precision, but this success didn't mean the underlying reality truly made sense or was properly understood. This persistent tension between having the ability to calculate something mathematically and genuinely understanding its nature runs like a thread throughout the entire history of physics. The revolutionary concept of a field was invented and developed precisely to resolve this troubling tension. To understand why this idea emerged, let's step back momentarily and consider a fundamentally different question. What exactly do we really mean when we speak of, quote, zero, quote? Conventionally, we declare that space is empty when there's an absence of matter within it. No atoms present, no dust particles, no air molecules, absolutely nothing. But is that truly the complete story, or does it oversimplify matters? Could it be possible that space itself possesses intrinsic properties even in the complete absence of any material substance? Imagine conducting this thought experiment. Place a small test object, perhaps a tiny electrically charged particle, at some arbitrary point in otherwise empty space. Now, carefully observe what unfolds. If that particle begins to accelerate in any direction, then logically, something must be exerting force upon it. You haven't placed any other physical object in its vicinity. Therefore, rather than claiming some distant object is mysteriously pulling on this charge through unknown means, you could articulate something fundamentally different. The space at that specific location exists in a particular condition or state. That precise condition is what determines exactly what happens to any particle placed there. This represents the first crucial conceptual breakthrough in understanding what a field actually is. A field is fundamentally not a physical thing sitting in space like a rock resting on the ground or a table occupying a room. Rather, it is a comprehensive description of the state or condition of space itself at every point. At each and every point throughout space, you can assign some specific quantity, whether that's a single number, a directional vector, or a combination of both. That reliably tells you what would happen if you were to place a suitable test object at that precise location. In the case of an electric field, that assigned quantity tells you the exact force that a charged particle would experience there. For a gravitational field, it indicates the acceleration that any mass would undergo at that position. Here's the remarkable part. You don't actually need the test object to be physically present for the field to exist in that location. The field is already there, existing quietly and continuously everywhere throughout space. This conceptual shift might initially seem subtle or trivial, but its implications are actually quite profound and far-reaching. Instead of saying the sun pulls on the Earth through space, you would now say the sun modifies and alters the gravitational field of the space surrounding it, and the Earth responds directly to whatever field conditions exist at its own specific location. The interaction between these celestial bodies is no longer some mysterious long-distance handshake occurring instantaneously across vast cosmic distances. Instead, it becomes fundamentally local in nature. The Earth only responds to and is influenced by what is happening in the space immediately right where it happens to be located. Why does this locality principle matter so much? Because nature appears to fundamentally insist upon it in every phenomenon we observe. Physical things influence nearby things first and foremost, and any influence or change takes a finite amount of time to propagate outward through space. The field concept allows precisely this kind of behavior. If the sun were to suddenly vanish into nothingness, a bizarre thought perhaps, but an instructive one for understanding, the resulting change in the gravitational field would not be felt instantaneously everywhere across the solar system. Instead, it would propagate outward at a finite measurable speed limited by natural law. Space itself would adjust and reconfigure itself point by point, region by region. Now, from a historical perspective, this revolutionary idea did not arrive fully formed all at once in someone's mind. It emerged gradually and slowly, pushed forward incrementally by scientists and thinkers who were attempting to make coherent sense of experimental observations that stubbornly refused to fit into the old conceptual framework. Consider the phenomenon of electricity as a prime example. Early experimental investigations revealed forces between electrically charged objects that appeared remarkably similar to gravitational attraction in their mathematical form. The forces grew stronger when objects were positioned closer together and became weaker as the distance between them increased. One might have stopped the inquiry right there and simply declared, quote 3. But experimental findings kept revealing increasingly interesting and unexpected phenomena. When charges were set in motion, they produced magnetic effects that hadn't been anticipated. Conversely, when magnetic conditions changed or varied with time, they produced unexpected electric effects in nearby conductors. The forces involved weren't just simple pushes or pulls, they had specific directional properties. These forces could twist compass needles into particular alignments. They could induce electric currents to flow in closed loops of wire. Something remarkably rich, structured, and complex was clearly happening in the space surrounding the charges themselves, not merely at the precise locations of the charges themselves. Consequently, instead of focusing exclusively on the charged objects as the primary actors, physicists gradually began to shift their attention to the nature of the space existing between them. Imagine performing this visualization experiment. Sprinkle countless tiny compass needles throughout the three-dimensional space near a permanent magnet. Each individual needle will align itself in one particular direction based on its location. Now draw arrows showing and representing those directions at each point. Congratulations! You've just created a visual picture or map of a magnetic field in space. Notice something conceptually important here. The field itself is not the magnet, nor is it somehow the same thing. The magnet merely serves as the source that creates or generates the field. The field exists everywhere throughout the surrounding space and possesses its own distinctive pattern, structure, and characteristics. Interestingly, you can even apply this thinking without involving magnets at all. Think about the concept of temperature as an analogous example. A room has a specific temperature value at every single point within its volume. You certainly don't need to place a thermometer at every conceivable location throughout the room to meaningfully talk about the temperature field that exists there. The thermometer merely reveals and makes visible what was already present in that space. In precisely the same manner, a charged particle, or a mass, functions like a probe or detector. It reveals and tells you what the field is doing, what value it has at that particular point in space and time. This analogy proves helpful because it removes some of the mystical mystery surrounding the concept. We're already quite accustomed to the everyday idea that space can possess varying properties, hot in this region, cold in that area. The concept of a field simply extends and generalizes this familiar idea to encompass forces and motion as well. But now, a deeper and more fundamental question naturally arises. Is a field merely a convenient mathematical tool or bookkeeping device, or is it something that possesses genuine physical reality? Initially, many physicists and scientists hoped and assumed it was just an elegant bookkeeping method. Instead of laboriously calculating forces between numerous objects in a complex system, you calculate and determine the field just once, and then simply observe how various things respond to its presence. That approach is certainly tidy, efficient, and mathematically elegant. But gradually over time, accumulating experimental evidence began to strongly suggest that fields represent something far more than just a clever computational trick. Fields can genuinely carry energy from one location to another. They can carry momentum and deliver it to objects. They can vibrate, oscillate, and propagate as waves. Most remarkably, They can even exist and persist in regions of space where there are no particles present at all. Light itself, something we interact with constantly, turned out to be nothing other than an electromagnetic field propagating and moving through space. Once created, no electric charges are required to sustain it, just the field itself oscillating back and forth in a self-sustaining pattern. This discovery represented a truly remarkable and revolutionary realization. What we had once conceptualized as absolute nothing, completely empty space, turned out to be fully capable of supporting wave phenomena, storing substantial energy, and transmitting influences across vast distances. Space was no longer merely a passive, unchanging stage upon which the drama of physics happened to unfold. It had become an active participant in physical processes, possessing its own properties and behaviors. At this juncture, it becomes quite tempting to pose the question, what fundamental substance is the field actually made of? Is it some kind of substance, a medium, or perhaps an invisible material filling space? This is precisely where we must exercise considerable care and caution. The history of physics is absolutely full of wrong turns and dead ends, caused by insisting too strongly that every genuinely new idea must somehow resemble an old, familiar one. People once seriously imagined a hypothetical substance called the luminiferous ether filling all of space, vibrating to carry light waves much like air carries sound waves through the atmosphere. That particular idea ultimately turned out to be completely unnecessary and deeply misleading, leading physics astray for decades. The field does not need to be physically made of anything in the ordinary material sense that we typically use that phrase. It represents a fundamental entity in its own right. Asking what it's constructed or made of may be philosophically similar to asking what numbers are made of. It's a category error. What truly matters for physics is not what the field is in some abstract philosophical sense, but rather what it does and how it behaves in different situations. Physics advances and progresses not by successfully naming the ultimate substance of reality, but rather by discovering reliable, testable rules and principles that connect observations to predictions. So, let's shift our focus to what fields actually allow us to accomplish in understanding nature. They enable us to replace mysterious, distant influences with comprehensible local interactions. They allow us to describe physical changes propagating through space at finite, measurable speeds rather than instantaneously. They successfully unify seemingly different and unrelated phenomena, electricity, magnetism, and light, into a single, coherent, and elegant framework. And perhaps, most profoundly, they force us to fundamentally rethink what we even mean by quote 6 or quote 7. But despite this progress, there remains something unsettling and troubling about all of this. If fields genuinely exist everywhere throughout space, even in regions we consider completely empty, then by definition, the universe is never truly empty anywhere. And if particles are merely things that respond to fields and are sometimes nothing more than excitations or disturbances of fields themselves, then perhaps the particles aren't the most fundamental actors in nature after all. This line of reasoning brings us to the very edge of a much bigger, more revolutionary idea, one that fundamentally changes how we think about matter, forces, and even the nature of reality itself. If space can possess fields as intrinsic properties, and if fields can carry energy, move through space, and interact with one another, then what exactly is a particle in this picture? Could it possibly be that what we casually call objects are merely special, localized behaviors of something far deeper and more continuous underlying reality? That question is not merely philosophical speculation or abstract wordplay. It fundamentally reshaped the entire landscape of physics throughout the 20th century. And once you begin to take it seriously and follow its implications, you can no longer look at empty space or at physical objects in quite the same way you did before. So, before we venture any further down this conceptual path, here's the crucial question to hold firmly in your mind and contemplate. If forces don't act across space directly as we once naively thought, and if space itself can carry influence, store energy, and possess intricate structure, then could it be that the field is actually more fundamental than the things we previously thought were doing all the acting? Let's pick up our investigation exactly where we left off that tantalizing question. If space can genuinely carry structure, energy, and causal influence throughout its extent, if it can exist in a definable condition at every single point, then we are logically forced to reconsider and question something we usually take completely for granted in everyday life. The assumption that discrete objects are the basic, fundamental ingredients from which the universe is constructed. After all, that's precisely how we instinctively and naturally think about the world around us. We imagine a universe constructed from countless little bits of matter, tiny particles flying around through space, occasionally bumping into one another, pulling and pushing through various forces. In this intuitive picture, fields are relegated to a secondary role, convenient mathematical tools, useful for calculations, but not really real in the same tangible sense as particles seem to be. Now, here comes the deeply uncomfortable part that challenges our intuitions. Modern physics, developed over the past century, quietly but definitively reverses that entire picture. Instead of starting with particles that somehow create or generate fields around themselves, it turns out to be far more accurate and fundamental to say that fields come first as the primary reality, and particles are what we happen to observe when these underlying fields behave in certain highly localized, quantized ways. That's an extraordinarily strong claim to make. So let's not rush past it too quickly. Let's carefully examine how nature itself pushes us toward this conclusion, step by logical step. Start by considering something familiar and everyday: waves propagating across the surface of water. You don't think of a wave as a thing that exists separate from the water itself. It's a pattern, a coordinated motion of the water medium. If someone asks you, quote, 10, the answer is remarkably simple: water. But the wave itself is definitely not a chunk or piece of water, traveling bodily across the ocean from one shore to another. The water molecules mostly stay approximately where they are, moving up and down. What travels is the pattern itself. Now imagine you observe a sharp, highly localized ripple moving rapidly across the water's surface. It's naturally tempting to treat it like a discrete object with a definite position and trajectory, but it fundamentally isn't such an object. It's a temporary, structured behavior of a continuous medium, the water. Fields behave in a surprisingly similar way to these water waves. An electromagnetic field fills and permeates all of space continuously. When it oscillates in a particular organized pattern, we give that phenomenon the name, quote, 11. When that oscillation is localized in space and quantized, meaning it can only exist in discrete packets of energy, We call those individual packets, quote, 12, but the underlying entity remains the electromagnetic field throughout. So when you detect a photon arriving at a specific point, what you are actually witnessing is not a tiny billiard ball-like object arriving at that location. You are observing the electromagnetic field interacting with matter in a discrete, quantized way at that moment. This is not merely a matter of interpretation, philosophy, or preference. It is forced upon us by experimental evidence that cannot be explained any other way. In quantum physics, particles stubbornly refuse to behave like solid, classical objects moving along well-defined trajectories through space. They spread out in wave-like patterns. They interfere with themselves in ways that seem impossible for discrete objects. They behave like extended waves until suddenly they don't, collapsing to points upon measurement. The only theoretical description that consistently works and matches all experimental observations is one where the fundamental entity is a field that's defined everywhere throughout space. And what we call a, quote, 13 is an excitation or disturbance of that underlying field. Every single type of particle in nature corresponds to its own specific field permeating all of space. There exists an electron field filling the universe, a quark field, a neutrino field, and fields for every other particle type. Even what we call, quote, 14 by this account is not truly empty in any meaningful sense. It is a vast collection of quantum fields all existing simultaneously in their lowest possible energy states. This is precisely why the word, quote, 15 becomes completely unavoidable in modern physics. You can certainly try to avoid using it or thinking in those terms, but the mathematics and the experimental results simply won't let you get away with it. Now, this realization raises a subtle but absolutely crucial point that deserves our attention. A field is not just a static, unchanging background painted onto space like wallpaper. It is fundamentally dynamic and capable of change. It can change and evolve with time. It can interact with other fields in complex ways. And most surprisingly and counterintuitively, it can fluctuate randomly even when absolutely nothing external seems to be happening, even when sitting in its lowest possible energy state. A quantum field is never perfectly still or motionless. It jiggles and fluctuates constantly at all scales. This isn't happening because of external disturbances or influences pushing on it from outside. Rather, it occurs because the fundamental laws of quantum nature strictly forbid it from being completely motionless and well-defined. This is not noise or error in our measurements. It is an intrinsic property of reality itself. So when we use the technical word, quote, 16 in modern physics, we don't mean absolute nothingness or void. We mean the ground state of all fields, a condition that still possesses structure, contains energy, even if minimal, and has observable consequences. This field-based understanding explains something that would otherwise be deeply puzzling and seemingly impossible to comprehend. It explains how particles can spontaneously appear and then disappear back into nothing. Under certain specific conditions, when energy is supplied to a quantum field from an external source, it can cause that field to produce excitations. What we observe as particles emerging out of what we would have once naively called completely empty space. Later, those same excitations can vanish back into the field, releasing their energy. But crucially, nothing is actually being created from absolute nothing here. The field was there all along, filling that region of space before, during, and after. Notice carefully how radically different this picture is from the old mechanical worldview of classical physics. Instead of a universe fundamentally built from tiny solid pieces like cosmic Lego blocks, we have a universe built from continuous entities, fields, with discreteness emerging only in how these fields are excited and how they are observed through measurement. At this point in our exploration, it's entirely natural to feel a little intellectually uneasy or even resistant. Fields are everywhere throughout space. They are completely invisible to our senses. They cannot be picked up in your hands or pointed to in the ordinary tangible way we point to objects. And yet, we are being asked to treat them as the most fundamentally real things that exist in nature. So how can we know with confidence we are not fooling ourselves with elaborate mathematical abstractions? The answer is clear, because fields do something very important that abstract mathematical conveniences cannot do. They make precise, testable predictions that no object-based theory can replace or match. They tell us exactly how fast physical influences propagate through space. They explain perfectly why electromagnetic effects travel at precisely the speed of light and not at any other velocity. They predict genuinely new phenomena, wave behaviors, electromagnetic radiation, interference patterns that are subsequently observed with extraordinary accuracy in laboratories. They unify forces that once seemed completely unrelated to one another into coherent frameworks. And perhaps, most tellingly of all, when we try to remove fields from our physical theories and talk only about particles interacting directly with one another across space, the mathematics becomes hopelessly inconsistent or completely meaningless. Fields are not an optional extra or decorative addition to physics. They are the fundamental language that nature uses to organize itself. Now let's return briefly to gravity, because it completes this picture in a particularly elegant way. Gravity was historically the very first force we learned to describe mathematically with precision, but it was ironically the last force to fully accept and embrace the field viewpoint. For a very long time, gravity appeared to be nothing more than a simple pull between masses, straightforward action at a distance. But eventually, accumulating experimental evidence and theoretical insights forced a deeper, more radical interpretation. Instead of describing gravity as a force acting through space from one mass to another, we now describe it as a property of space itself, specifically as the geometry or curvature of spacetime. Mass and energy don't pull on distant objects. Instead, they change and modify the geometric structure of space and time in their vicinity, and objects move in response to that altered structure. Once again, the influence is fundamentally local in character. An object reacts only to the condition and geometry of space-time where it happens to be located at that moment. In this profound sense, gravity is not even a quote 18 in the traditional Newtonian meaning of that word. It is a manifestation of a field, one that defines what straight lines even mean, what time intervals are, and how geometry itself works. So whether we find ourselves talking about electricity, magnetism, light, or gravity, the underlying message remains consistently the same across all phenomena. Space is not a passive void or empty container. It possesses intrinsic properties. It responds to matter and energy. It evolves dynamically over time. And now we reach a genuine turning point in our understanding. If fields are truly everywhere, and particles are excitations of those fields, then the universe is fundamentally less like a mechanical machine made of separable parts and more like a continuously active system structured by mathematical rules and laws rather than by discrete pieces. This new understanding doesn't make reality vague, fuzzy, or less precise in any way. On the contrary, it actually makes it considerably more precise and well-defined. Fields obey exact mathematical equations that can be written down explicitly. Their behavior is constrained by strict laws. They don't do whatever they like arbitrarily. They do precisely what the laws of nature demand they must do. But this field-based perspective does fundamentally change how we should think about physics. Instead of asking, quote, 19, we now ask, quote, 20. Instead of asking, quote, 21, we ask, quote, 22. And once you genuinely adopt this field-based viewpoint in your thinking, a remarkable thing happens to your understanding. Many long-standing mysteries stop being inexplicable mysteries altogether. They transform into natural consequences of field behavior. So here's the question that naturally emerges next, and it is the one we cannot avoid or sidestep if we want to go deeper into understanding reality. If the universe is fundamentally made of fields rather than discrete objects, if particles are just special disturbances or excitations of something continuous and ubiquitous, then what does that profound realization say about matter, about identity, and about the very idea of things existing at all? We began this entire exploration with a simple discomfort and unease. Physical objects seem to influence one another across empty space without touching, and for centuries no one could quite explain satisfactorily how this happens. That persistent discomfort turned out to be not a weakness, but a valuable clue pointing toward deeper truth. By following it carefully and patiently, without rushing to conclusions, without hiding behind mathematical formulas and pretending we understand when we don't, we were led systematically to a quiet but genuinely radical idea. Space itself is not nothing at all. It has structure and properties. It has definable conditions at each point. It can carry influence from place to place. A field is our scientific name for that structure, the way space is organized. It is not merely a trick for making calculations easier, and it is not some ghostly substance floating mysteriously between solid objects. Rather, it represents the way nature fundamentally organizes cause and effect in a local manner. At every single point throughout space, something concrete is defined and present, and physical objects, when they appear in our observations, respond only to what is happening where they are located. There's no mysterious reach across vast distances of the universe, no instant messages transmitted through nothingness at infinite speed. Just space behaving in a particular rule-governed way at each and every location. Once we accept this field-based framework, the old mechanical picture begins to dissolve and lose its grip on our thinking. Particles stop being conceived as tiny, solid actors pulling invisible strings from afar. They become events, localized, quantized behaviors of underlying fields. Matter is no longer the foundation of reality. It is a manifestation of something deeper. What we instinctively thought were fundamental things turn out to be patterns in a continuous medium. This revolutionary insight does not make the universe less real or substantial. Quite the opposite. It makes it more coherent and comprehensible. The same fundamental idea that explains magnetic attraction and the nature of light also explains gravity and even the geometric shape of space and time itself. The same conceptual framework that describes supposedly empty space also explains why it is never truly empty, but filled with fields. What initially looked like a bewildering collection of separate, unrelated phenomena becomes a single, connected story with common principles. And perhaps the most important lesson we can draw from all this is not technical at all, but philosophical and methodological. It is a profound lesson about the nature of understanding itself. Nature does not care one bit about our intuitions, our preferences for solid objects, or our desire for simple pushes and pulls that match everyday experience. Physical reality does not arrange itself conveniently to match our immediate sensory experience or common sense. But nature does offer us something considerably better and more valuable than comfort. It offers consistency. If we are willing to follow the logic carefully wherever it leads, if we can accept ideas that feel strange or counterintuitive at first encounter, then the pieces fit together into a coherent whole. So the next time you imagine or contemplate empty space anywhere in the universe, remember this crucial insight. You are not looking at nothing whatsoever. You are looking at the most fundamental stage on which all of reality unfolds and plays out. It is active, intricately structured, and quietly doing all the real work behind the scenes. And once you truly see and understand that, the really important question is no longer what are objects made of fundamentally. Instead, it transforms into something far deeper. What kind of universe makes fields possible at all?